So now we're going to take a look at a common mode rejection ratio example to kind of get a better grasp on this complex topic. So what we're going to want to do is we're going to want to calculate our common mode rejection ratio for a particular circuit, a particular difference amplifier. And we're going to want to calculate that in decibels, dB, for a difference amplifier. I'm going to just abbreviate that as difference amp. And we're told for this particular difference amplifier, we have R2 over R1 is equal to 10, and R4 over R3 is equal to 11. So let me clean up this 3 a little bit. And so of course we know that for an ideal difference amplifier, the ratio of these resistors is the same, but here we see it's just ever so slightly off. Because our R4 over R3 ratio is a little larger. So what we can do is we can actually go back to the equation that we had when we were first introducing our difference amplifier. We said that the output voltage is equal to, we had R2 over R1, and then we had that times some weird fraction where we had 1 plus R1 over R2, and that was divided by 1 plus R3 over R4. So we had something that looked like that. That was times all of that multiplied by V2 minus R2 over R1 times V1. So what we can do now is we can substitute in these values here, and we just need to note that in our equation down here, of course, we have R1 over R2, which is just the inverse of R2 over R1. Same thing in the bottom here, we have the inverse. So we're just going to, instead of putting 10, we'll of course put 1 over 10, and in the denominator for R3 over R4, that's going to be equal to 1 over 11. So we're just going to plug in our values. So we say R2 over R1 is 10, then we have 1 plus, now R1 over R2 is 1 over 10, and in the denominator we have 1 plus 1 over 11. All of that was multiplied by V2. We subtract then minus, so minus R2 over R1 is minus 10, and we still have RV1. So if we plug that into our calculator, we get that this is 10.083 repeating times V2 minus 10 times V1. Okay, so for our common mode rejection ratio equation though, we need our differential gain and our common mode gain, but here we just have this V2 and V1. So we need to manipulate this equation a little further, and so we're going to do that by remembering our equations that V2 is equal to our V common mode plus VD over 2, and our V1 was equal to V common mode minus VD over 2. And so remember we described that graphically with our V2, our V1, our V common mode, and our VD, if that helps you remember these equations a little better. So at any rate, we can plug in for V1 and V2, and then we're going to get our expression in terms of V common mode and VD, and then ultimately we can relate that to our general expression to get our differential and common mode gains. So what we're going to do is we're going to substitute in this V1 and V2, so we're going to take our V2 and put it right here, and our V1 and put it right here. So doing that and simplifying, well, let me go ahead and write out explicitly what that looks like here. So we have 10.083 repeating times, we said V2 is V common mode plus VD over 2 minus 10 times V common mode minus VD over 2. So now if we factor out our terms there and we collect like terms, we'll get our V0 is equal to 10.0416 times our VD plus 0.083 times our VCM. And so now this looks like that general form for our difference amplifier. We said that was V out times AD times VD plus ACM times VCM. So essentially now what we're going to do is we're just going to pull out our AD and ACM terms from this equation. to get our common mode rejection ratio. So let me just circle this so we can see explicitly. So this number here is our AD, and this number here is our AC. So now we can plug in to find our common mode rejection ratio in decibels. So common mode rejection ratio in dB is equal to 20 log base 10 of 10.0416 divided by 0.083. So we plug that in, and it's going to give us approximately 41.65 decibels. So that would be our common mode rejection ratio for this difference amplifier. So like I said, typically for a good difference amplifier, we're going to want that to be a little closer to 100. So good differential amplifier, or difference amplifier, is going to be CMRR in the range of 80 to 100 dB. So we see that this amplifier isn't quite great, so definitely not ideal, and falling short of that range for our good difference amplifier. So let's say we had some slightly different information. Instead of knowing the value of these resistors from the get-go, maybe instead we don't have access to that information, but we can play around with the inputs to the circuit, measure the outputs. How would we get our common mode rejection ratio from that information? Well, so let's say that very same circuit is simulated in PSpice. And so I'm going to write the results here, and we're going to go from there to see if we can get the same final answer. So same circuit simulated in PSpice, or as I was saying, maybe it's a physical circuit that's wired up, and we have access to the inputs and outputs, so we can change inputs and measure outputs. Either way is the same. So let's say we have our inputs sort of for test 1. We do inputs of V1 is negative 50 millivolts, and V2 is positive 50 millivolts. So this I'm going to call my test 1. So that's going to result in an output, of course a single output because we just have one output V0, of 1.0043 volts. We then do a second test case where we have V1 equals V2 equals 5 volts. And so in this test 2 scenario, this is our test 2 input, we find that our output is Vout equals 0.4153 volts. So this is a good opportunity, again, if you want to pause the video and try to think about how to approach this yourself. I would encourage you to do that. Okay, so what we're going to want to do is try to find that common mode rejection ratio again. And hopefully it's going to end up being the same as what we calculated by hand, knowing the resistance values, or the ratios of the resistance values at least. So let's look at our test 1 case first. So from our test 1 case, we have that our differential voltage, VD, which is equal to V2 minus V1, is going to be equal to 50 millivolts minus a negative 50 millivolts, which is 100 millivolts. We can also write that as just 0.1 volts. And our common mode is going to be the average of the two. So we have V common mode, which remember we defined as V1 plus V2 over 2, is just going to be equal to 0. So basically they're centered on 0. And these ideas look a little different if we're talking about for AC circuits, but the same basic principles apply. Okay, so remember in general, we had that our output, and so let me write in general here. So in general, remember our output is equal to our differential gain times our differential voltage plus our common mode gain times our common mode voltage. Well, in this case, our common mode voltage we know is equal to 0. So what we can say then is if we know that 0, then we know that our AD is equal to our output voltage divided by our differential voltage. So our output from test 1, coming back up here to our results, we see was 1.0043 volts, and our differential voltage we calculated to be 0.1 volts. So we calculate our differential gain to be 10.043 volts. Sorry, it shouldn't be volts, dimensionless. Okay, so now let's look at our test 2. So for test 2, we have our differential voltage. We're going to do the same type of thing, still defined as V2 minus V1. But now we see V1 and V2 are the same, so we have 5 minus 5, so our differential voltage is going to be 0. And now our common mode voltage is equal to V1 plus V2 divided by 2. Again, V1 and V2 are both 5, so we get 5 volts as our common mode voltage, which we would expect because 5 volts is what's common between the two inputs. Both of them have that same value. Okay, so then we can come back to our general expression. So we can say in general, we have our output is equal to our differential gain times our differential voltage plus our common mode gain times our common mode voltage. And so in this case, we now have our differential voltage is 0, which is going to mean we'll be able to solve for our common mode gain. So doing that, we can say our common mode gain in this case is equal to V out over V common mode. So coming back up here, we see for test 2 our output was 0.4153. So 0.4153 volts, and our common mode voltage we calculated to be 5 volts. So we see that our common mode gain is 0.08306. So now we just plug into our equation and we can find our common mode rejection ratio in decibels. So that's equal to 20 log base 10 of 10.043 divided by 0.08306. And if we plug that in, we get approximately 41.65 decibels. And so that is the same number that we got with our hand calculations, so everything checks out as expected. This is a complicated topic, so if you do have any questions, don't hesitate to let me know.